2. So today we're continuing on and we're starting chapter 2 in today's lecture. Chapter 2 focuses on matter, atomic structure, and the periodic table. So let's start off with our discussion of matter, everything that matters. So chemistry as a field focuses on the study of the composition, properties, and transformation of matter. Matter is anything that takes up space, has volume, and has mass. So for the states of matter, let's look at things first from the macro scale perspective. These are materials that we can see and manipulate. So intuitively, when we think about solids, so like a table, what we notice for solids, they generally have a fixed shape and a fixed volume. Liquids, such as, for example, a glass of water, they have a fixed and defined volume, but liquids will adopt the shape of their container. We can pour liquids into different containers and their shapes will change. Gases are unique in that they adopt both the volume and the shape of their container. For example, you can take a gas and put it in a balloon, and the gas is adopting the shape and volume of the balloon container. Now, as chemists, we're far more interested in the particulate scale. Remember, matter is made of fundamental particles known as atoms. And at our particulate scale, we're looking primarily at atoms and molecules. For in a solid, when we look at our microscale picture of a solid, what do we notice about our atoms? Are they close together or far apart in our solid picture? Are the atoms close together or far apart?
Close together.
Exactly right. In a solid, the particles are closely packed, and I like to think like they're vibrating in place, shaking in place. There's not a lot of molecular motion, relatively speaking, in a solid. The particles are fixed, they're close together, they're vibrating in place, they're closely packed. If we look at our liquid picture at an atomic and molecular scale, are our particles close together or are they a little bit spread apart? Are they closely packed or are they loosely packed?
Loosely packed.
Exactly. So for a liquid, the particles are loosely packed, and as a result, our particles can slide past each other. This additional freedom of movement is what gives liquids their variable shape. So the particles can slowly slide and move past each other. And there's a little bit more freedom of motion in a liquid. If we look at our gases, are particles close together or are they really far apart? Looking at this picture for our gaseous sample, are the particles close or far apart?
Far apart.
Very far apart. For a gas, the particles are heavily dispersed, and as we have these little speed lines to indicate, these gas particles are just constantly bouncing about. In fact, in the room around you, you have gas particles that are moving at quite high speeds, bouncing off surfaces, moving past each other, and in a gas, the atoms and molecules are very far apart. And the particles, most importantly, are rapidly moving. Okay, so we start to see a link between the microscale properties, how the atoms are arranged and how much freedom of motion our atoms and molecules in our sample of matter have, to the bulk physical properties. That is the goal of chemistry, to connect the microscale, the atomic and molecular scale, to the macro scale, which is what we can see with our eyes. Okay. So let's talk now about atoms, molecules, and elements. So matter is composed of fundamental particles called atoms. Atoms can be bonded together, can be linked together to form molecules. Now, the central creed of chemistry is the composition of matter determines the properties of matter. And by studying the fundamental particles that make up matter, we can understand the behavior of matter. This viewpoint is also known as reductionism. So let's talk about atoms. So atoms are the smallest unit of an element that has the properties and reactivity of that element. Now, how do we parse this? Well, the classic example that I like to use is lithium metal. So let's suppose we have a sample of lithium. If you've ever seen some of these chemistry enthusiast videos, people love to record YouTube videos where they drop alkali metals into water. So if you drop lithium into water, what you're going to see almost immediately is a large generation of heat, and you may even see a fire. So we know that bulk lithium, a bulk chunk of solid lithium, reacts with water. Now, if we look at an atom of lithium, if we think about a lithium atom, if we react a lithium atom with a water molecule, we would also see a similar pattern of reactivity. The lithium atom also will react with water to generate heat. So, an atom is the smallest unit of an element that has the properties and reactivity of that element. This giant piece of lithium, if we zoom into it, if we zoom in, we would see contains an array of tightly packed, as it's a solid, an array of lithium atoms. So the bulk properties of your element will match the properties of your atom. So an atom is the smallest unit of an element that has the properties and reactivity of that element. Does that make sense to everyone? Does this idea make sense? Perfect. So for a molecule is the smallest unit of a pure substance containing two or more atoms bonded together. So for example, water. So we have hydrogen and oxygen. So water is written out as H2O. Now, as we can see in our formula and in our picture of water, we have two different symbols, and that tells us we have two different elements. And further, because we have more than one atom, because we see more than one atom, that in turn tells us that we have a molecule. Anytime we have two or more atoms bonded together, we have a molecule. They don't necessarily have to be different elements in a molecule. For example, nitrogen has two atoms of nitrogen bonded together. So when you think of the word molecule, I want you to think two or more atoms bonded together. Now, what is an element? So an element has been empirically defined as a pure substance that cannot be chemically decomposed to a simpler component element. So for example, if you start with hydrogen, which is H2, no matter how hard you try, you're never going to get a simpler element than hydrogen. Now, element names and element symbols are each unique, and each element name and symbol are derived from isolation, their Greek name, or their Latin name. So each element has a unique symbol. The symbol has 1 to 2 letters, and the first and only the first letter is capitalized. So for example, CO represents cobalt. It's really important that you only capitalize the first letter. Capital C, capital O does not represent cobalt. In fact, it represents a compound known as carbon monoxide. So make sure you're only capitalizing the first letter for each element symbol. Each unique element has a unique symbol containing 1 to 2 letters. Does this make sense to everyone so far? Is everyone comfortable with this idea so far? Okay, so let's talk about these elements. So the periodic table is really the cornerstone of chemistry. It's going to be your central reference throughout this semester. And that's why I provided you in these notes pages containing full-size periodic tables with different pieces of information. Now, the periodic table, and the reason why it's such a wonderful reference, is that it organizes elements based on their properties and reactivity. So the periodic table is deliberately organized and sorted such that different regions, rows, and columns of the periodic table correspond to different patterns of reactivity. So let's talk about the major divisions of the periodic table, denoted by these 3 colors. So metals, we've handled them in our day-to-day lives. These are shiny, ductile species that conduct heat and an electric current. Metals are overwhelmingly located. Where do we see our metals on the periodic table? Are they on the top or the bottom of our periodic table? Where do we see these where do we see our yellow metal tiles? Where do we see our
Left part.
Yes, they're located on the left side of the periodic table, and they're also on the bottom. And as some of your classmates have noted, almost the majority of elements in the periodic table are metals. So metals are located on the bottom left. So I like to draw an arrow pointing down and to the left, and I write an M for metal. Non-metals. So non-metals, let's look at our non-metals now. Non-metals are dull, brittle, and they don't conduct heat or electric current. Non-metals, where do we see non-metals in the periodic table? On the left or the right-hand side?
On the right.
On the right-hand side. One exception to that is hydrogen, and I want you to remember, hydrogen is a non-metal. It acts like a non-metal rather than a metal. Non-metals are located in the top and right side of the periodic table. So I draw an arrow going up and to the right, and I write the letters NM for non-metal. Now, metalloids are really quite interesting, both from a chemical perspective and for what they've done for our society. If you own a cell phone, you likely have encountered and dealt with metalloids in your day-to-day life. Metalloids have properties between a metal and a non-metal. Many metalloids are also known as semiconductors. Metalloids are located between the metal and non-metal regions of the periodic table. So I like to draw this diagonal starting from boron. And that is a nice little mnemonic to memorize the 5 major metalloids, and then also include antimony as well. So there are a total of 7 metalloids, and a nice mnemonic to remember our metalloids is just to draw a horizontal arrow from boron to a tellurium. Metalloids have properties in between a metal and a nonmetal, and they lie in the region of the periodic table between our metals and nonmetals. Any questions on these major divisions of the periodic table? Any questions on the major divisions of the periodic table? Does this make sense to everyone so far? You'll have to be familiar with classifying elements as metals, nonmetals, and metalloids. Now, I'm going to show you now the type of periodic table that you'll be provided as a reference on most exams. So this is known as the IUPAC periodic table. Notice how it's not labeled with any of the color coding for metals, nonmetals, and metalloids. So the first thing I'm going to do now that I have my periodic table is I'm going to draw out and put a box around my metalloids. There we go. So now that I have my metalloids clearly boxed, I know everything to the left of that is a metal, everything to the right of this is a non-metal. I always like, whenever I have a reference and I have some information that I can add to my reference, I always write on my reference, write on my periodic table, add that information, just so that way I don't have to spend as much time recalling that information later on. I've already set up my periodic table to help me through my problems. So let's do an example where I'll start us off. We're asked to identify which of the following elements are metals. So, okay, so looking at the periodic table, I see lithium. That's on the left-hand side. That's a metal. Selenium, nope. Cobalt on the left-hand side. That's a metal. Argon, nope. Boron is a metalloid. Calcium on the left-hand side. So that's a metal. Okay, so I've circled all of my metals. Next, we're asked to identify which of the following elements are non-metals. So nitrogen, looking at nitrogen, it's on the right, so I'm going to circle nitrogen. Carbon, carbon is also on the right, so I'm going to circle carbon. Sulfur and chlorine as well are also on the right-hand side of the periodic table in the non-metal section. Aluminum, nope. And helium, yep, that's a non-metal. It's technically known as a noble gas, but it falls in the non-metal region of the periodic table. Okay, now we're asked to select each metalloid. Okay, so looking at our metalloid section, the only metalloid that we see is boron. So I'm going to circle boron. Any questions on these examples? So given the periodic table, we are able to read the periodic table and identify which of the following elements, based on their symbols, are metals, nonmetals, or metalloids. Does this make sense to everyone? Any questions? Okay, so let's try to apply what we've learned. Here's a fresh IUPAC table. And then I'd like you, using your reference periodic table, to identify in the following list which elements are metals, in the following second list which elements are non-metals, and then from the previous two, I'd like you to select each metalloid in the previous two lists. Let's take about 4 minutes to work through this example, and then we'll discuss momentarily. And don't be shy if you have any questions to submit your responses in the chat or to unmute and ask your questions verbally. And let's try to get a few more responses in the chat, and we'll discuss in about another 2 to 3 minutes. And the responses I'm seeing in the chat look good so far. Remember, this region in the middle of the periodic table also contains metals. And we'll discuss this example in another minute to a minute and a half. Okay, so let's discuss this example. So from our metals, everything on, so I'm going to draw my dividing line once again for my metalloids. So looking at our metals, we see we have beryllium on the left-hand side. Iron is also on the left-hand side. Potassium is also on the left-hand side. What about hydrogen? Is hydrogen a metal or a non-metal? Is hydrogen a metal or a non-metal?
Non-metal.
Exactly right. Perfect. So for our next list, we have a list of elements. We're asked to identify which of these elements are non-metals. Okay. So phosphorus meets that list. Arsenic is a little bit special. Arsenic is a metalloid. Continuing on, oxygen and fluorine. Oxygen and fluorine are also in the non-metal section. And argon as well is also in the non-metal section, as well as krypton. So as I alluded to, when we're selecting each metalloid, as your classmates have astutely pointed out, tellurium and arsenic are the metalloids from our following list. Does this make sense to everyone so far? Does this make sense to everyone so far?
Yes.
Perfect. So what I'd want you to start working on is I'd like you to start to get familiar with, and I'd like you to know the names and symbols and start to begin to memorize the names and symbols of element numbers 1 through 36 as well as iodine. You're not going to be tested on this immediately, but the more familiar you are with the name and symbols for these first 36 elements, it'll make the next part of this chapter, as well as the subsequent chapter that we're covering on nomenclature, substantially easier. So it's start sort of getting familiar with and knowing the names and symbols for these first 36 elements, as it'll serve you well in the next few lectures in this class. So that's it for today's lecture. So